So I want to talk about this interesting article, Language to Logical Form with Neural Attention. And before that, I just want to remind you that data could be in a SQL database, but nowadays we put it on graph databases such as great databases such as Neo4j. And it could be NoSQL. I have worked several years on MongoDB and those NoSQL databases. So it depends on your database. You could have a different way to retrieve it. So you need a different mechanism for semantic parsing. Because semantic parsing is a framework. It's not a method, as I have explained in previous lectures. So there are some great articles to think about. I will explain all of them in this lecture and in some of my lectures in future. But today I just want to focus on this article from Li Dong. And I can show that this is related to this picture, but I will explain this interesting article, which is about Lambda DCS. We call it Lambda. It's a simplification of Lambda Calculus, because sometimes the data structure is simple enough to just remove some complex stuff and make it simple. And this article, I like this article as well, because first of all, it is written by Percy Leung, a great researcher, and also because he has used that approach for Freebase for question answering. So these are amazing, they are amazing scholars, and you need to learn all of their articles, I guess. Very interesting ideas. And so what is first order logic? I don't want to talk about all of the logic, just a quick review. A restaurant near CMU, Carnegie Mellon University, serves Indian food. So we can write it as there exists a restaurant of X, so this is Boolean, so it could be either 1 or 0, because X could be near a restaurant. For example, X could be a restaurant. For example, X could be a shop, but it's not a restaurant. It could be a place. It could be a house, but it's not a restaurant, so it becomes 0. It should also, X, we rate this as like this. X should be near CMU, Carnegie Mellon University. So if X is near Carnegie Mellon University, then this Boolean expression is just 1. And also another one, X serves Indian food. So if X serves Indian food, we put it 1. So and of all of these becomes the final answer. So it's Boolean expression. And we say there exists such X such that this 1 is true. There is something. Or all expensive restaurants. When we say all expensive, though, for all X, we say this is negation. Or far from, it means that it's near, so it's negation. And Lambda Calculus you can see it as a variant of high order logic, and it is invented by this American mathematician and computer scientist Alonzo Church. Of course, Alan Turing, that British mathematicians had the same ideas, but Alonzo Church invented this Lambda Calculus. Arguments could be functions and not just entities. So, in Lambda, in Python programming, in JavaScript, all of those nested functional things that we work in our companies. So all of them are related. So you can also use them because if you have practiced them before. So it's not a new thing. We are just representing them. because as you will see, machine understands this easily because machines work with databases. It works with web if you are developing semantic web, which is a great area of research. And so for A, we move A, and then A and the direction of left, and so on. So we can reduce our lambda expression, let's say. So instead of saying X is near Carnegie Mellon University and we feed it with some input, we say that if this input is near Carnegie Mellon University. So they are the same things. This expression is the same as this expression. So we call it Lambda Reduction. So we have a sentence, for example, your voice, but as a speech recognition, it translates it to some text. And then you give it, after some steps, you give it to semantic parser. It understands the meaning, hopefully. And it executes on the robot. For example, go to the kitchen and bring me some coffee. And the robot should understand what is a kitchen. Oh, human needs some food, needs coffee, and it exists. The coffee machine is in the kitchen. And so that's why people... So in just 1 second, your chatbot should think about all of these things and give a response. For example, go right, this is geolocation, this is the location of that, here we are, so we should go right and then straight. But there are something, we have dependency parsing and we have semantic parsing. Don't confuse. You see, syntactic is like finding the dependencies in a sentence. For example, this sentence, what is related to what? For example, we say, I will explain in another lecture about dependency dependency parsing and those things. For example, this could be head and these could be related. Even they could be related, for example, S1 related to S2, sentence 2, via and. And each sentence could be a complicated tree because we don't like loops. We don't like. So I will explain syntactic things, which is dependency, which is the context of dependency parsing in computational linguistics. And it's very important for question answering, for text summarization, for lots of applications, such as even coreference resolution. But we have another thing which is called semantic parsing. You know, when you say go to the kitchen, those things, and see if we have some fruits, it should look at the database of the kitchen, and so the fridge is just another database. If there is all of these, so all of them are some databases. They could be SQL databases or NoSQL databases, or could be even graph databases. So it should translate to something meaningful. Meaningful being semantic. It has a semantic meaning. And Lambda Calculus, a quick recap is like this. For example, X, city of X. X goes to city of... Think about it as a function. Just like all functional programming you do in JavaScript, in Python, all of those beautiful codes. Now it is written in a formal language, a formal logical language. And this is called predicate. It's a logical expression located in. Oh, by the way, in knowledge graph, for example, we can say Tehran is located in Iran. And we have arguments, list of logical expressions. For example, Austin is located in Texas. And examples of typed lambda, it could be typed as well. It has a type as well. And so we say X is a flight. Yes, X is a flight, list of all flights. And So it goes to a database and find a list of all flights. And also, X should go to New York. So from all, or just write a query in SQL database, for example. If X goes to New York, find all those things from that database, those things. So if it is 1, then we've got everything. And this is called constructor types. It could be simple or complex. And another example of Lambda Calculus, we say, for example, at the chair, move forward 3 steps past the sofa. And we write it like this. And there are 2 types of grammar, context-free grammar. And the good thing is that there are non-term parse tree nodes are non-terminals in context-free grammar. In combinatory category grammar, CCG, there are categories. And in CFG, we have part of speech tags, but in CCG, we have categories. So slightly different. An example for CCG. And so the traditional approaches rely on high-quality lexicons, manually built templates, and linguistic features, which are either domain or represent. But we aim to use a simple yet effective method to bridge the gap between natural language and logical form with minimal domain knowledge. So this article, Language to Logical Form with Neural Attention, is just using these Lstm. And so we give some sentences and we give some logical forms, and so that your chatbot or voice bot could understand. So our aim is to learn a model which maps natural language. We have a sentence like or even question like x1, x2, xq. And we just say that we don't want this sentence. The robot understands the interpretation. It's the logical forms of that. It understands the logical forms of that. And we are just maximizing this conditional probability. So PA, given your question, is like this. So our method consists of an encoder. So it encodes it into just a vector representation, as usual. And we have a decoder which translates those, which generates y1 till ya, conditioned on your encoding vector. And so we describe 2 models varying in the way in which P of A given Q is computed. The first model is sequence-to-sequence model using LSTM. Everything is as usual. But here, E is index of corresponding token. And we are learning W. And for the decoder part, which gives the output the predicted, the logical forms, it gives us the logical form, is this. But we use softmax as usual because this is a conditional probability. What is the probability of this logical form given the previous logical forms? And so this is, and the motivation for changing sequence to tree model is that the sequence-to-sequence model has a drawback because it ignores the hierarchical structure of logical forms. Oh, by the way, when I talk about dependency parsing in a future lecture, you don't need all of these things. It implicitly captures all of these things, so you don't need to worry about the tree, because the dependency parsing in its essence has some dependency tree, has a tree structure, so we don't need to worry about the things. And this is the sequence to tree model. And they use a technique called parent feeding connection. That the hidden vector of parent non-terminal is just concatenated with the input before getting to feeding into Lstm. And another model is attention mechanism. I think they're just copying the transformer model using the tool, the components of Lstm. So I don't think any point of this, because you could use transformer. Maybe because transformer is not good for... No, that's not the reason. But I don't know why they are doing this, because they are just capturing this context vector that is already very beautifully implicitly existed in the transformer. So that is the attention score, because we need a score, and using that S with this attention score for the case. This is for the case hidden state. And just a linear combination of that gives your context. And we do model training as usual, but here D is just set of all natural logical, because Q is natural language sentence, A is the logical form, so all of these pairs, give it to it, maximize the likelihood, and because it's the log of multiplication becomes the summation, and then you minimize it because you convert maximum likelihood to minimum loss. In machine learning, we want to reduce the loss. And here P of A given Q is written as this, and we, as I said, we transform it to softmax because it's conditional probability in order to learn the weights. And at inference time, we just see which one maximizes the output from several options that you could possibly choose. So, given your question, you want to maximize which of your possible options maximizes this P. And this is the algorithm for inference time. And this is Alonzo Church, the founder of this Lambda Calculus, which goes by 1933, I guess. But at that time, we didn't know that in future we will invent language and computational linguistics become so important. Of course, this is like semantic parsing, not dependency parsing. So this Lambda Calculus can be used for, at least for semantic parsing in 2022 instead of 1930. So he had something in mind, like the ideas of Alan Turing, very futuristic ideas. But now we can implement all of these things. Of course, a Lambda Calculus is really complex. That's why that barely, I will explain in the next lecture, in the next two lectures, I guess, about the Lambda DCS, a simplified version of that. If it has a nice simple structure, if your database has some simple structure, you could use Lambda DCS to remove some redundancies, something that are not necessary, and reduce those some of those words.